Okay, welcome back everyone. In this video we're going to talk a little bit about what simple harmonic motion is, and it's important to study because it helps us understand really what's going on with waves. So first we'll start with the definition, and so simple harmonic motion which you're often going to see abbreviated as SHM, is basically any situation where an object is acted on by what we call a restoring force. So restoring force means that it tends to push the object back towards equilibrium. So this restoring force pushes the object back towards equilibrium. So there's a lot of examples of things that occur that are periodic but aren't necessarily simple harmonic motion. But here's a good example of SHM. Okay, so in this picture you have a mass on a spring, and so what you do at first in the top view is you stretch out the spring, and the spring is going to exert a force to the left which tries to bring it back to the unstretched length, which is this dotted line here. Then it's going to compress the spring, and that force is going to point again towards equilibrium. And so basically this will continue as long as there's no friction, and the mass on the spring will oscillate back and forth. Okay? Another example of simple harmonic motion is a pendulum. So if you have a mass on a pendulum, of course you're going to have tension as one of the forces, but gravity is really what's going to cause a pendulum or a swing to go back towards equilibrium. And so if equilibrium is right here, like right here, then part of gravity is going to go to be opposite of the tension, and part of it is going to kind of be a restoring force. And we're not going to get into too much of the details of that, but just keep in mind that anytime you have simple harmonic motion, you're going to have a restoring force. Now, one thing that's interesting is that most restoring forces can be written somewhat like this. So, for example, a spring force is equal to some constant times a displacement. So that's what delta x is. So this is the displacement from equilibrium. I'll abbreviate that. And what about for the negative sign? Well, what does that mean? Well, if we go back to our picture, when the mass is to the right of the equilibrium point, x is positive, but the restoring force is going to be negative. It's going to pull us back the other way. Likewise, when we're sort of to the left of the equilibrium point, x, the displacement, is negative, and so the force will be in the positive direction. So there's always kind of an opposites thing going on here, which is why we have that negative sign. And that's what actually restores the object to equilibrium. If we don't have that, it's not going to move back to the 0 point. Okay, and this particular one for spring is sometimes called Hooke's law. So K is a spring constant, and this can show up in other forms as well. You could have something where you have, we haven't even talked about torque, but something twisting back and forth, like if you go to the playground and you sit on a swing and you kind of twist it around and then let go and it unspins. So that's kind of like a twisting restoring force. So there's lots of different examples. And just a quick reminder of some of the terms that we've talked about. First of all, the amplitude, which you may have already seen in a previous video. The amplitude, which we write as an A and has a unit of m, is basically the distance from equilibrium. and it's a maximum. So it's the maximum distance from equilibrium. The period, again, is a capital T, and this is the time for one cycle of motion. Oops, one cycle of motion or one oscillation. Okay, and one question for you. How far does an object travel in one period? Think of this in terms of the amplitude. So think about this for a moment, pause the video, and when you're ready, go ahead and unpause it. Okay, so if you think about simple harmonic motion, it does kind of make a sine, kind of a sine wave, and if we think about the position versus the time, we're going to have something that looks kind of sort of like this. So how far does something go? Well, this is the amplitude. So we have to go out to the maximum amplitude and come back, so that's 2a, and then we need to go the other way and come back. So it's a total of 4a is the distance that something travels in one period. Now if I said what's the displacement, that would be a different story. We know that the displacement in one period should be 0. Okay, and finally, just as a reminder, the frequency is the number of cycles per second. And so frequency is an F and is measured in hertz, which is the same thing as 1/seconds. Okay, so for example, if we have a spark timer at 50 hertz, that means it's making 50 sparks per second. And once again, the relationship between frequency and period is that they're inverse. Okay, and you might also see the frequency written as the Greek letter nu, but it looks too much like a V, so I use an F. Okay, so that's about it for this time.